but we can talk about two different categories. We say let C and D be categories. Who cares about my handwriting? Let C and D be categories. Okay, and you can talk about so it's not a function between sets like it was morphisms in the category sets. But it's a generalization of that called a functor when it's a function between categories. So, uh, a functor between category A or C and category whatever D. Where the fuck I wrote it. So a functor between two categories. So guess what? That means that this F for every object in A. Well, what does this mean? A functor. So this is called a functor. So now I'm like talking about two different categories. One, they could be a subcategory, in which case the functor is just the inclusion. It's a subcategory, but you could be talking about different categories. I mean, one could be groups and one could be topological spaces. That is a study of algebraic topology or algebraic topology. Yeah, can be summed up as a functor from two special categories, two of the most important categories. We're assigning invariance to on one side. The functor is assigning invariance. So now we're talking about two categories. So, but remember, what was a category C? What was a category D? They both have to have their set of objects and pairwise morphisms for all their objects. So that a functor from C to D, for every object in E. So let A be so this is an object in C. This has to map through F to F of A, which obviously has to land in the object. This has an object. This has an objects and morphisms. Remember, that's what a category is, or maps, objects and maps. So an object in A, and this one has to land, has to be mapped to an object in the second one. This is natural. Sorry, I have the mistake. Fucking clubhouse on this. Sorry. So I gotta map objects to objects, and I gotta map morphisms to morphisms. So that's what a functor would be, to properly take one category into another one. For every object, I have to do this, and functions and morphisms in here, which I can sum up as a function, basically. And I can write it as either any of these two, as F is a function or a morphism in the category from A to B, or I just write A to B with an arrow and call the function up here F. You see how these two are the same thing? Look, I mean, it's the same information. It's the same. One is a function from A to B. It's just a different notation for writing a function from A to B, or a map from A to B. So to pass it through the functor from category C to category D, you got to not only take objects from category C to category D, but you got to take functions to functions from so F of A gets mapped to F of A. Well, what does B get mapped to? F of B. So the functor has to assign to that F. So the functor applied to F has to be a function from the functor applied to A to the functor applied to B. But actually, this is a covariant functor. If you reverse all the arrows, you go into the opposite category. It's a contravariant functor. But they're equivalent to just symmetric. You just to every arrow, every category. That's another statement. Every category. If C is any category, it has something called C op, called the opposite category corresponding to every category C. And all C op is the opposite category is just imagine the category C with every arrow reversed. And I told you the whole thing could be embedded into a giant graph of arrows of everything, and where you have multiple arrows if you have multiple maps from in a certain. But it could be all. So the category op is the opposite category. It has a rigorous definition, but you just think of it as it's the category. Any category I can consider this. So if and what happens going up here in this category, or in this category of sets, my initial object was the empty set. If I consider set op, so if sets the category op, if I consider this category, then where this guy will be the. So we got to map. I'm explaining what functors are. You got to take objects from category C to objects of category D, and then likewise you got to take morphisms, because that's what C was built out of, objects and morphisms. you got to take morphisms from to their respective things. So another way to write this here, another way to write this was F was a map morphism. F was a map from A or maps, doesn't matter, from A to B, right? That's another way to write any of these two statements. F is a map from A to B, or F is a function from A to B, or this is the same. This is another way to write it is this way. That has to correspond to F of F in. So this is so usually when I've been neglecting writing in every hum set, usually you use hum, but for simplicity and writing maps, just to keep it morphism so that nobody gets confused over. I'm again I'm not trying to sound smart. I'm using as simple words as I can. Well, when we were talking about different categories, you have to be specific of the maps from A to B in the category of sets could not be the maps from A to B in the category of groups. If A and B are groups, every function is not a group homomorphism in the set. So you got to specify. So this is this. You have the C here. This is the set of hom. You write hom from C from A to B. To specify. So F in here has to map to some F in hom. Well, what depends if it's a direct, if it's a covariant functor, because there's two covariant or reflecting all the arrows, reversing all the arrows. If it's a covariant functor, then this is if it was contravariant, it would take hom AB, it would take this hom AB to hom BA to F of B minus and F of A. It would just reverse them. It reverses everything. But if it's covariant, then this is F of A to F of B. And so and this is the same thing as saying that that's just a fancy name for a function. So it's morphism. A functor takes categories to categories by satisfying these conditions. Takes objects to objects and morphisms to morphisms. And I guess let me let people in, and I can now because this is among where we wanted to go to understand. Well, we're probably not even done understanding categories, but you guys gotta unmute yourself. Let's stop sharing.